Hello and welcome back to ST118 Statistics and Applications, Session 5. In this video, we will examine the three or more population medians test. Another name for that is commonly called the Kruskal-Wallis test. So let's dive in. That's our three population medians test. There was a discussion using the parametric method of test, and that's called the ANOVA test. And if you haven't seen that, it's probably a good idea to have a look at that video to understand that we are looking at three population parameters, right? In the ANOVA case, we use the mean as the center of gravity to represent each population. And in this Kruskal-Wallis test, Kruskal-Wallis test, we will use the population median, right, to form our hypothesis and statistical conclusion. Okay, and of course, we certainly want to talk about an example illustration to get a feel of how the test number crunches the data, right? So it's always helpful to see the numbers being processed, and it's not that we want to do it ourselves repeatedly, but I think it's educational to have a feel of how the numbers are being done, at least even if that makes you ask another question that is already doing its work of inspiring you to probe, into the understanding of the mechanism. So here we want to first formulate the purpose, right? The purpose is to test whether the three population medians are the same. And so we want to form a hypothesis, right? Essentially, we want to say eta 1 equals to eta 2 equals to eta 3 equals to dot 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 eta k. Right. So what we want to do is, and you can already sense that there's probably a limitation. What we want to do is eta 1 equals to eta 2 equals to eta k. There are k populations, right? At these one group, right, has differs in median. So this would be very analogous to the way we phrase the mu1 equals to mu2 equals to mu k in the ANOVA case. The Kruskal-Wallis test, right, is what is both useful and matches closest to what we want. So in other words, I need to be very clear here. It's not exactly testing the medians, but as an indirect consequence, we get to test the median. So what exactly are we testing? We are testing that the populations, the population distributions, the population distributions under the null hypothesis are all the same versus at least one group differs in the distribution, differs in distribution. Now, what is distribution? Distribution is the shape, right? So when you imagine you have the ability to measure all the measurements in the population and you plot the histogram, the resulting shape. So normal bell curve is what we are talking about. So we are assuming that all the measurements, all the populations come from the same distribution. The distribution share the same form and shape. Well, this then implies that all the medians, and by the way, all the means are also the same. Even the shape is the same. Okay, so it's like bell curve, bell curve, bell curve, bell curve. All are bell curves. Or uniform, uniform, uniform. All are uniforms. So once the shape is shown to be the same, then necessarily all the medians will be the same. So that's the indirect comparison. So just keep this in mind, right? Even though what we want to test for is this, the non-parametric equivalence method for ANOVA. Okay, so let's get started with generating some test data. So we have first sample, right? We get first sample to be 2, 5, and 7, let's say, right? Sample 2 can be 1, 3, 4, and 6. Sample 3, because we need to have 3 or more groups, so this is the least I need to go in order to illustrate the Kruskal-Wallis test, right? And of course, I intentionally have different sample sizes to show that Kruskal-Wallis, just like ANOVA, can deal with different sample sizes. So this is 4, and clearly this is 5, just to note. Okay. Then what we want to do is, of course, you can, if you've gone through the videos on Wilcoxon signed rank test and Mann-Whitney test, you would have seen the ranking exercise, right? The ranking exercise. Okay, so what we are going to do is to rank the data. Okay, so again, we are going to put them together. So the data, we're just going to put the data, merged data in some sense, right? Merged, combined data, much like in the Mann-Whitney exercise. So we have 1, 3, 4, 6, 3, 8, 9, 10. Okay. Now, of course, we can delineate with some helping markers to tell us they are from different samples. Okay, so once we have merged them, we can perform ranking. Okay, so here I didn't sort them, so that ranking is a little bit, we got to be careful. Just make sure we can rank the values, right? And then untie it, just like what we did in Wilcoxon and Mann-Whitney, right? So untie the ranks to make sure that the ranks, for example, 3 and 3, right? We did see a 3 and a 3. Make sure that it is the rank associated with one of the 3 and the other 3, you know, we need to average them out. Okay, so we see what to do. So we rank. So we put in the rank, that's our rank. So let's do that. So we put in the rank. So value 1 is, of course, gets a rank 1, right? Value 2 gets a rank 2 because there's no duplicate. But soon as we say that, we see value 3 having 2 occurrences, right? So this is actually rank 3 and rank 4. Either way you put it is rank 3, rank 4, whatever. All right? So 3 and 4, we want to average them 3.5 and then associate them with both these numbers, because we can't distinguish which one should get 3, which one should get rank 4. So we get this. So 3 and 4, ranks 3 and 4 have been used up. The next number, number 4 here, should get a rank 5. Right, 3 and 4, they are used up already. Then anything higher, 5, right? So 5 here will get a rank 6. Then 6, 8, there are 2 6s. Suppose we get rank 7 and 8, right? So we'll average them to get 7.5. So ranks 7 and 8 have been used up. They replace the two ranks. So 7.5 replaces ranks 7 and 8. Then after that, we get 7, I think. Okay, so here 7 and 8 have been used up. So rank 9, rank 10, rank 11, rank 12. So not too bad. For small sample sets like this is extremely small, right? 3 measurements. If you calculate the sample variance, sample standard deviation, this is barely enough. Not very good at all, right? So, but we're not trying to be getting high precision, high accuracy like in real life. We're just trying to illustrate calculation concept. So we do the ranking, and then you have minimally 3 groups. Already this gets to 12, is that right? 12 numbers, right? And manual calculation starts to get a little bit unwieldy. But we will, we still can cope with it, and so we continue. Next, we calculate the rank sums for each group, right? So what we're going to get is that we get the first rank sum, R1, right? We add up these guys. Okay, so the Ri's are the rank sums. So 2 plus 6 plus 9, that's going to give us 17. Then for second group, we get, adding these up, right? We should get 17 as well. 10, 11, 12, 17. The rank sum for group 3, if you add them up, we should get 44. Yeah, 44. Okay, so once we get these, we need to combine them to get the H test statistic. The H test statistic, that's the Kruskal-Wallis test statistic, is given by H. Okay, so this is the test statistic. Is H equals to 12 of n times n plus 1. This n is the sum of n1, n2, and 3. So the total sample size. So summation of all the rank sums squared over each sample size, right? So I equals to 1 to k, where k is the number of groups. So we have 3 here. Minus 3 times n plus 1. This is one term by itself. Okay, so well, let's get going and see what happens. So our h here, using the numbers, we actually get, let me clarify, right? So here n equals to n 1 plus n2 plus n3 plus nk. K is number of groups. So h is actually 12 over our n. Our n is 3 plus 4 plus 5, 7 plus 5, 12. Right, so 12, 13, right, n plus 1. Sum of 17 square over 3. Right, so 17 square over 3 plus 17 square again. But we know this is not reusing R1, but this is R2 over 4. That's why you see, you know, this is different R2, not R1. And 44 square over 5. Right, so this is what it's trying to say, the summation. The whole thing is the summation. Then after that, once you finish the summation, you have a 3 times 12 plus 1, 13 here. Okay, and the whole thing, and I'm not going to do primary school mathematics here, will evaluate, right, to 3.7526. Okay, degree of freedom is k minus 1. Just like ANOVA, right? we have k minus 1. So 3 groups. 3 groups minus 1 is 2. So we need degree of freedom and alpha to find from the critical values, right? So the critical value, let me come back to here. Okay, so critical value is taken from chi-square distribution of degree freedom k minus 1. Okay, so let alpha equals to 5%. Then what we have is chi-square of alpha, comma degree of freedom, gives us 5.991, right? And we can then compare, right? So what that means is that chi-square, right? Chi-square distribution is a well-studied distribution. So we can do a quick display of chi-square starting from 0, and it's going to be like that. Okay. And the 5.991 is what is it? 5.991. Okay, so it's here 5.991. So this is our chi-square distribution critical value, and it is actually a extreme value, right, on the right side. So chi-square. So the rejection region is on the right side, even though it sounds like a two-tailed test. So rejection region like here. Okay. Now remember what's our H naught? Population distributions are the same, right? But when one group differs, then some sort of error or variance occurs greatly because it's creating a lot of error squares, and it will push the Google pin very, very far to the right if the group is very outstanding, differs by a lot, or multiple groups differ by somewhat certain magnitude, large enough magnitude, right? So altogether, the error square is very large. It will push the Google pin into the rejection region and then force us to reject H naught and conclude that something strange is going on, right? So that's the way ANOVA goes as well, even though that was using F distribution. By the way, chi-square and F, they are very related. Chi-square is a special case of F distribution. So you can see the close relationship here. And well, we have our test statistic, don't we? We have 3.75, right? So roughly we can say it's somewhere here, 3.7526, right? So the Google pin doesn't go into the rejection region, and the p-value is going to be largish, right? So we have the alpha of 5% here, and our p-value after because it's chi-square distribution, we can certainly tap on the chi-square CDF function, such as chi.dist in Excel, or p chi pchi in R, to find out the region here, the probability here. So the p-value that I get is 0.1532, thereabout. But we know it's already 15, right? 15 means do not reject. Google pin 3.75, also less than 5.99, so do not reject. Basically, do not reject. Yeah. So we'll say that since, right? So since, and this is the standard distribution. Standard because it's chi-square, very well known. Since, so we use the p-value because we really trust our p-value to be very exact. Since p-value is equal to 0.1532 and it is not less than alpha equals to 0.05, we do not reject H naught. So if we do not reject H naught, we retain H naught and look at what H naught says in English. No Greek letters, no etas, no mu's, no sigma square, right? So just state it, right? Population distributions are all the same. And conclude that all medians are the same, because median is actually our point of dispute when we started off this discussion, this investigation, this calculation. So we are less interested in the fact that the shape, that means Kruskal-Wallis gives us a conclusion that is even more than what we want. All we want is that the medians are the same, right? But Kruskal-Wallis says all the distributions are the same. That means including the shape, the means, the skewness, everything are the same. So it's a lot more than what we want at 5% significance level. Okay, so that's the conclusion we derived from this calculation. Okay. So, well, let's just basically I'm done with my example, but I want to kind of illustrate what's the big deal, or what's the difference here, right? Population distributions are the same versus population medians are the same. So what's the contrast here? I mean, what point is made by saying the words differently, right? So here, under the assumption that population distributions are the same, right? Distributions are the same. So under the assumption that population distributions are the same. So let's draw two population distributions, right? One is, let me try to use something that is light. Okay, one is the bell curve, let's say. So bell curve. And not so bell, because I purposely have some wrinkles there, like that. Okay, because most likely in practice, and if you're using non-parametric methods, these are probably finite and don't stretch to below 0 or above certain large value. Certainly doesn't touch infinity, right? So this is one distribution, and the other distribution could look like this. I'm going to draw a sort of a dotted line. Doesn't mean less important or silhouette or whatnot, but kind of tracing to similar shape, except certain wriggling they are permitted because of statistical noise, right? Not, yeah. So in other words, it's to say that population 1, right? Population 1 has this shape, and population 2 has this shape, and yet, despite the minor wriggles or gaps here and there, those are statistical noise, right? Anyone looking at these two curves should agree with me that they are similar distribution. So we would then say they are exact, they are the same, except for a bit of statistical noise. That's why we go through these calculation steps. Otherwise, we just compare the shape, right? They must match. Some little gap will say different. But that's like very robotic. That's very black and white. That's not statistics. So that's why statistics, we allow for some wriggling room to differ a little bit. But of course, if the gap starts to get larger and larger, then it will cause Kruskal-Wallis to reject. So the good thing is there is no assumption of normality for Kruskal-Wallis. So the shape doesn't have to look like this. It can be any crooked shape, bimodal, whatever it is. It doesn't have to even be lumpy in the middle, roughly symmetrical, that kind of thing. First thing first, I already finished with the finite bounds here, which is definitely not normal, right? Okay, but just for understanding's sake, what is meant by population medians are the same, right? So this implies automatically, right? Implies, what's a good color to use? Implies automatically that all population medians are same. Yeah, okay. So if the distributions are the same, then you can conclude that all the means are the same because the two shapes are overlapping. The medians are the same, skewness are the same, kurtosis are the same. All population parameters are the same because they're indistinguishable population distribution. Okay, so if you, for example, measure the population and you plot histograms for one batch of year one statistics students score results, and then you plot the same again for next year's, right? So different people, right? But they are all graduating from high school, college, and then admitted here, and they're taking the same statistics course, maybe even doing the same exact exam questions. Hopefully, the questions didn't leak, right? Then it won't be surprising to find that even for different individuals, right, in the class, in the course, in the cohort, the distribution of scores will end up being, statistically similar. Now, the claim that all populations or the two population medians are the same does not imply that the distributions are the same. So let's try to draw another chart here, or two population distributions here, right? Where we can have one distribution looking like this. Okay, first thing first is the medians are the same, right? So median. So the median for population one. Okay, so the median for a bit, this is tail, so here. So median eta 1 and eta 2. At most, they differ by a little bit, right? So close that the gap between eta 1 and eta 2, no difference. So here I want to, of course, nail down the eta. So eta 1, the population median for population median for population 1, and eta 2, population median for second population. So both are the same, having the same value 100, right? So maybe the other one is 99.99 or something. So both are 100. Now, the first population can look like this. All right. And the second population can look like this. Okay, I try to estimate the median to be half area, right? Half area. Right? So roughly speaking, the pink population, the population 1, has half on the left and half on the right. And the red population also, I think, roughly, right? 50% here, 50% there. So I hope visually it's convincing to say that both medians are the same. But I think everyone screamed, right, that no, the shapes are very different, right? So true. Okay, very true. Now, what happens to Kruskal-Wallis when we apply Kruskal-Wallis to this? So when we apply Kruskal-Wallis to this, here Kruskal-Wallis will not reject H naught. All right, allowing us to say that all the medians are the same because the shapes are the same within statistical noise boundaries. Here, Kruskal-Wallis will look at the shape, right, and say, wow, okay, so no, right, reject, likely reject. Very likely. Likely because it all depends on the finer details, right? Very likely, I would say. Very likely, it will reject H naught, forcing us to conclude that the medians might not be the same. So this is the kind of wrong conclusion. So you want to be aware of it. You want to be aware of it so that when it is rejected, there is a small chance, right, that the medians overlap. Even for very drastically different looking distributions, the medians need not differ by what in the context could be very alarming kind of difference, right? So maybe it's not a big gap. After all, if right our interest is in testing whether the medians are the same. So this is the sort of a contrast to show. So we can complete the sentence here. Population medians are the same. So given, right? So given this implies this. So given this implies this. Given that the population medians are the same, does not imply that the population distributions are the same. Right, as is very obvious in this illustration. Okay, so I hope you get to become more careful, more aware of whenever Kruskal-Wallis test does not reject H naught, right? Then you can safely conclude that all the population medians are the same because it's a very strong do not reject. Once you do not reject, Kruskal-Wallis is telling us a lot of information, much more than what we want. All that we want is that all the medians are the same, right? But Kruskal-Wallis is saying, not only that, actually I know that all the distributions are the same. So which implies what we want. However, when Kruskal-Wallis rejects the H naught, it is telling us that the shapes don't match at all. Okay. In practice, when the shapes don't match, there's good chance, right? I don't know what's good chance. Maybe more than 50, maybe 60. But those numbers don't matter so much. As in, there's a not very little chance. Okay, there's a good chance that the medians don't overlap. They are not very close. Right? So that we are most of the time safe. So when Kruskal-Wallis rejects by the distribution shape, it is likely that it is also correct that the medians are not the same. Okay, likely. All right. Again, not the same means they are not close. But then how close is considered close depends on this scale here, right? If this is 0 to 1 million, then a gap of 5,000 is also considered very close. But if this is 0 to 10 here, then a gap of 1 is very big difference, isn't it? Yeah, so we need to be very careful of this very last case when Kruskal-Wallis rejects H naught, okay, and we are so at that point we are very sure that the distributions don't look alike. Then we need to be extremely careful to not immediately jump to the conclusion that therefore eta 1, eta 2, they are different. We need to be very careful with the conclusion. All right. Now, of course, then we ask, can we, if we have two populations, then certainly we can use two population median tests, right? Mann-Whitney, Wilcoxon, paired unpaired tests to test this out. Most likely Mann-Whitney test to test whether these two etas are the same. So in fact, we won't come to Kruskal-Wallis in the first place if we only have two population medians. The thing is, when you have more, right? When you have more shapes, another one. Okay, so something like that. Okay, now the median here is very strange, right? It's at almost the trough of the whole distribution. So when you have more distributions, all looking different, then where is the conclusion that all the medians are looking different? In fact, they're all the same, right? But this will be getting smaller and smaller chance. That means the distributions look so bizarrely different, and yet all the medians are exactly very, very close and bunched up together, right? I did this because I engineered it to be so. I constructed it by first fixing all the medians to be there, then I draw the. But then in real life, things don't happen this way. Things happen the way they happen for populations 1, 2, and 3, and then you calculate or you check the median, right? So under that kind of situation, you are like asking the hundreds or millions, maybe even, right? The measurements or the particles or the measurements or the numbers to align in such a way that the three medians are overlapping on top of each other. Just think about the probability of that happening by chance, right? And it shouldn't be by human construction. There should be some statistical element, some randomness, some natural, uncontrollable. Maybe it's by human, but by other people, not you, the observer, the experimenter, right? So much so that it's hard to imagine that so many measurements, right? By time, by measurements, by nature's influence and everything. After everything, you kind of do this descriptive, you find that they are the three medians or even more if you have more populations, 3, 4, 5 medians all exactly overlap on top of each other, right? So that kind of probability is not, I mean, nothing is impossible, but very, very small. So much so that when Kruskal-Wallis rejects H naught, we have good chance to believe that the at least one median is different, which is not wrong, not too far off a conclusion. At least one median is different, right? For all the medians to overlap on top, it's very rare, although not impossible. But this needs to be in your mind, just so that you are careful before you make very daring assertions or conclusions. Okay, so with that, I come to the end of this video. Thank you very much for your attention, and see you in the next video where we discuss more exciting aspects of hypothesis tests.